I'll go through at least some of the bits now. So there's one way of using it here, and here is a thing saying, can you use the std generate algorithm to do this for you? So the standard way is to go look at the documentation, because I can never remember exactly what the order of arguments is. So it's the first to the last, specify the range, and then it's the generator. And the generator is a thing that, when called with no arguments, will return a value that can be copied into the iterators pointed to thing. So that's easy enough. We've got our generator here, takes no arguments, and it returns an integer. So I can go something like generate nums begin nums end den. Okay, or I could just, of course, take this and pop it in there. Okay, so to sort it, it's going to be std sort, and this takes a range, because sorting is something you use a lot. I actually know this one. And if I wanted to sort in some different way, I would need to provide a lambda here, but because I just want to sort numerically, that's fine. Okay, so we can output those things. Now we want to reverse this. So just using it directly, we use std sort on the same range because it's the same data. And now we need to produce a lambda, and it's going to work with integers. If I could type const f, and it would help if I had a name for these. So we need to provide an operation that's the opposite of less than, so it's going to be greater than, and we return a greater than b instead of a less than b, which would have been the default. Yes, so someone who knows the standard library has pointed out that I could just use greater. So the standard library includes function objects that act like greater, less, equals, plus, minus, all the built-in arithmetic operators. So there's a big list of them here: plus, minus, multiplies, divides, blah, blah, blah. Bitwise ones, logical ones too. Which is pretty handy. I chose to write it myself. It should be exactly the same, but if you wanted to do it, you would go greater on int, and then you would have to create one. Because std greater angle brackets int is a type, you need to actually instantiate the type to create the function object to pass in. And if instead of doing that, let's reverse it again. There is actually an algorithm called reverse. And you just pass it your range. And that will do exactly what you think it will, reverse your range. Okay, so this one is doing a sort of a simple example. Oh dear, I must have done this in a much wider editor. So let's get the fist 47 Fibonacci numbers using std transform. Okay, so we have our uninitialized data. We've got space to store it, but it's not been set with any numbers. We need to go set the first one to 1, and the second one also to 1, because that's how we bootstrap the series. And then we need that fibs n, let's do it like this, n plus 2 is equal to fibs n, the previous one, and the one before that again. So using std transform is a pretty good way of doing it, because you need to take two ranges, which are actually parts of the same one, just offset, and you need to add them together and then store that result in a different position, which is actually the next part in the range. So we need one of the input ranges. Let's start at the beginning. So we're going to do this term first. And then we need to think about our end. If we were to go all the way to the end, then our output range would be 2 elements past the very end. So that would be an error. So we need to stop 2 before then. Then our other input is also part of fibs, but it is 1. It starts 1 after. At every position, it's the next one along from where fibs is. So we increment that by 1. Then our output is also in fibs, and that one is 2 elements on from the first one. Let's start splitting these over some lines so I've got some idea of what I'm writing. And now we need our, what do you call it? We need our function. So since we had these brought up, we can see that there's one for plus as well. So let's look at plus. Okay, so we can just use that std plus and create one of these things. Oh, okay, so we keep going, Okay, get all of the ones that are less than or equal to 4 million and store it in fibs less. Okay, use copy if and a back inserter. Okay, so that's fine. So copy if is enough. So we need to have our range. And now I need to know what is the order of the arguments. Okay, so copy if, it's this one. We've got our input range, our output range, and then our predicate. Mohammed did something else instead transform. Do you wish to paste your code? Is prime okay, so so you're transforming fibs from all the way through to the end, and you're capturing what has primeness got to do with anything here? I really don't understand. No, the Fibonacci numbers are not prime. So, I mean, I think it's defined at Project Euler on the URL given there, but the Fibonacci numbers, I've given the definition here. So the first one is 1, the second one is 1, and the one after that is and then following that, it's the sum of the previous 2. Yeah, sorry about that. It's just sort of, it's one of these mathematical sequences that I just take for granted that anyone with a sort of scientific background would have heard of. Sorry, apologies. Yeah, I suggest you just look up the definition and have a crack at that one again in your own time later. Okay, so back to the copy if. We've got our input range, our source of data, and we need to think about where are we going to store these results and what our condition is. So the condition is pretty easy. It wants to be less than or equal to 4 million. And we need to return true if it is less than or equal to 4 million. So if x is less than or equal to 4, 1, 2, 3, 1, 2, 3. And having a return statement would be good there. Sorry, it was just someone had sent a private chat message. I was just checking that. Okay, so we need our lambda. Let's make that a bit more readable. Taking an integer, and we're returning if it indeed is less than or equal to 4 million. So I have got the right number of zeros. Okay, copy it. So what do we do instead of the fibs left? So the code is suggesting using back inserter. And I mentioned this briefly in passing, and this is a convenience function template that creates a back inserter type for the container that it's called with, and it can be used to add elements to the end of the container. So every time you write a value to it and plus it, it will go ahead and call pushback for you. So it will do kind of what we want. So we need a std back inserter. On fibs less. That's probably going to work. Now get the even ones, the same as again. So evens is a vector. We're going to copy if some condition. Christoph asks, wait, what? Feel free to go voice to answer your question if typing's. The Fibonacci number sequence does grow very quickly. So that's thousands, millions. It's 3 billion. I'm pretty sure the 47 is chosen such that it will still fit in a 32-bit integer. Ah, does it overflow? Interesting. Oh well. Let's see if it overflows for me, and then if it is, then I'll have to eat my hat. I think people have different views about what the first one is. Maybe it is 0, yeah. Let me think. I'd probably have to go and check, but I'll believe you it's 0. I didn't check, I have to admit, before starting writing this. Okay, yes, people who actually checked the definition before writing code, well done. Always a good idea. Okay, evens. I'm going to need to copy from the fibs less instead of from fibs. And I'm going to back insert onto evens. And I'm going to return if the value is indeed even. If the modulus with 2 leaves no remainder. And now let's make a sum. So we can use accumulate, which I'm pretty sure is actually in the numerics one rather than. If you're in 17, you could use reduce as well. This is good, except it doesn't promise to accumulate, makes the promise that it will do each addition in order, whereas reduce doesn't promise any particular order. This is good if you want to be fast because it opens up the ability to do a bit of parallelization in the implementation or vectorization, but let's just use accumulate for now. And so if you want to use the obvious thing for your type, which is plus, operator plus, you don't need to specify a binary operation. But if you do want to specify what the function you're reducing over is, then you can specify that as a binary operation of your own. So is it a monoid these things form if you have a type, a set of values, an identity element, and a binary operation maybe forms a monoid or something. I'm going to start reasoning about these things. Okay, let's sum them. So std accumulate. We've got our range, which is our evens. And we have our initial value, which is 0. And then we can see that accumulate is going to return our answer as its return value. And so we can just remove that there. Okay, so let's, how many errors have I made? Quite a few. Nice. What's it complaining about? Oh dear. IO stream, undefined. What? I'm just going to check I'm actually logged into Archer on this one. Yes, you're probably right. I've probably forgotten to. Yeah, you're right. Okay, so it compiled and ran. Does anyone want to check my answer for me? Has anyone got the same thing? 4.6 million-ish. Yeah, that's because I reversed it twice. So I reversed it once and then reversed it twice. Okay, so I will, like I said, I will push all my solutions to the GitHub the end of the day, and I'll just push them onto a branch so you don't accidentally spoil them if you're coming back to this at some later date. So let's see, let's go away from that. Let's talk about linear algebra and arrays and stuff like that. And this is really the first bit of library that, or a library code that's not part of the standard library that I'm going to talk about today, because one of the big omissions for the scientific technical computing HPC world, the big omissions of the standard library is, and the language, is there's no multi-dimensional array support. Okay, so Fortran, this is what Fortran is good at, right? Managing large rectangular arrays of data and doing some maths on them very quickly. And even though I do not personally enjoy writing Fortran, I will not deny that it is very effective if you are doing a lot of linear algebra, a lot of dense array manipulation stuff. And the code that it generates is of a high quality if you've got one of the good optimizing compilers. So this lecture is written by originally by Chris Richardson, who's sort of an RSE software engineer type at Cambridge, and he gave this lecture the first time, one of the first times I gave this course for you know, sort of this type of audience through Archer down in Cambridge a few years back. So thanks to Chris for this material, the first draft of it at least. So what is Eigen 3? So it's a C++ library for matrix arithmetic, and it's what's called a header-only library. This means that you don't have to compile and install stuff to make it work on your machine. You don't need to go and ask the Archer 2 help desk to say to go and install this for every compiler version that's in there. You can just download the library and use it, or you can go, it is available on Archer already. So you can see that it's there, it's version 3.3.8. I can't remember how up to date that is, but it's not too old if it's not, certainly. And what this does is it fills in some of the key missing features that are needed if you're going to be doing some scientific computing using C++. And the library authors have done quite a lot of hard work to get good performance out of most high performance oriented processes. It's got a very simple to use interface, support for both dense and sparse matrices and vectors, and what it calls an array, which is a two-dimensional block of data of uniform type that does not multiply in the way a matrix does, but is in most other ways equivalent to one of its matrix types. And it has some support for basic solvers, which, given a known matrix A and a known vector B, will solve the equation A dot x equals B for you to tell you what x is. So you can just download it from the URL there. If you've got it on your own Linux machine, you can apt-get install it, whatever. And the comparison to NumPy is, well, not unreasonable. So let's have a look at a very basic use of Eigen here. So I've got you need to first include it. And if you want to be dealing with dense matrices where there's a bit of data allocated for every element in the matrix, you want to be using the dense file. So include Eigen/dense. Then this is one of these types. So you can see that the matrix thing is clearly a template. And in this case, we're using 3 parameters. The first parameter is the type that it's going to contain. So this is a matrix of doubles. You could equally well use ints or whatever custom type you like. And then I'm specifying the size of this. And here I'm giving a fixed known at compile time size of 10 by 10. Let's call that A. And then I'm using this member function called set0. You can guess what it does. And now I'm setting one particular element, 9,0, to be some number. And now you can ask cell this to be printed. So you can use C++'s preferred stream insertion operator, binary left shift. And this will print a representation of your array to the stream. Okay, so, it's not a million miles away in the way you would access it from a C-style multi-dimensional array, but we have a bunch of extra member functions that any member functions, because of course a C-style array doesn't have any. You can use these member functions, and instead of using square brackets twice, you use round parentheses with both indices given to access it, to access a member. So if you want to use a size that you don't know at compile time, so maybe you're going to read the size of your arrays from some setup file or something, or you're going to compute them in some way that's non-trivial to do at compile time, you can use a dynamic sized array. And if you want to do that, you have to pass this Eigen : dynamic tag type, it's called. So it's a special value that when you pass it into the matrix will become resizable. And this means that when you want to instantiate one, you need to give it the sizes, unless you want it to be default constructed to have 0 size. But then you can resize this at runtime whenever you want. So we've set it up to be 64 by 65, and then later on we want to resize it to a square 20 by 20. And so you can output things. So here I'm getting the number of rows and the number of columns. So hopefully that should be fairly clear what's happening there. And this is much more like std vector than a std array, which is perhaps what that previous one was like. So in the library provides a bunch of convenience aliases for you to use. So typing Eigen matrix angle double comma 3 is going to get boring quite quickly. So there are various aliases or type defs, you might call them, for commonly used ones. So a matrix 3 lowercase d means a 3 by 3 matrix of doubles. For integers, the suffix is I, so that's a 3 by 3 matrix of ints. If you want to have dynamic, then it's a x instead of a number. And then for vectors, you have vector x for dynamic and d for double. And then if you want a row vector, it's well, a row vector. So that's one with a single row and a number of columns. And so if you've got some of these instances, you can start doing some matrix maths. So if we've got matrices A and B of whatever sizes, A is 5 by 10, B is 10 by 2, and you've got a vector with 10, we can do things like say that C is equal to A times B, and at runtime, in this case, because they're dynamically sized, the Eigen system will check that the sizes are compatible and then get on and do the matrix multiplies for you. And the same for this vector W. I'm going A dot the vector. It's going to check that the sizes are compatible and get on and do it. And then it will construct that into there and store your result there. And so you've got dot and cross products for vectors, transposes, the usual sort of scalar arithmetic things, anything that you could do with a mathematical matrix and vector. And if you want to do element-wise operations that perhaps would not be what you would naturally do with a matrix in the mathematical sense, let's do this. So you can always take a matrix in Eigen and take a view of it as if it was an array by calling this dot array member function. And what that does is that returns an Eigen array type that holds on to the same data. So the underlying data storage of this thing is exactly the same, but you're offered a different set of operations on it. So here, I'm setting every value to 2. And because in most sort of conventional mathematical views, the sign of an array is not defined, you cannot do that. But Eigen allows you to perform these operations in an element-wise fashion on arrays. So if I take B and look at it as if it's an array, then take the sign of it. And then I can assign that into A's contents. But now if I have one of these arrays and try and do a matrix multiplication, a multiplication between the array and the matrix, that will give us a compile time error because this is an illogical thing to do, to try and multiply an array with a matrix. And another thing you can do, which is particularly handy, is you can take a view of some other data that's not allocated within by Eigen inside a matrix or an array, and view it as if it was one of these types. So for example, you could use a std vector to hold your data, to own your data. So any type that gives you a contiguous block of data. And then you can overlay an Eigen array or matrix on top of that data to get Eigen's API, but on top of data that you are managing some other way. So if we create a vector with 1,000 elements, we can then map this data onto a matrix of doubles, and it's going to be of size 100 by 10. So we can see that the sizes have to be compatible, and you've got to take some care about that yourself, because Eigen cannot check this for you, because all you're passing in this case, is a single pointer to the start of the data. And so Eigen will know that it's not owning this data, it's just viewing it. And so you can now start accessing it through Eigen's nicer API, at least nicer if you're treating it as an array in this, or matrix, sorry, in this case. So here we're viewing it as a fixed size array. So this means that we can the code that's going to be generated for doing arithmetic operations is going to be able to take advantage of the fact that the array bounds are known at compile time. And then for this other one, we're doing a view of it as runtime determined size. So in this case, we have to provide to this constructor of the map, we have to provide the information about what the sizes are in each direction, the number of rows and number of columns. So, okay, good question. Yes, I'm sorry that wasn't clear enough. Yes, so this is using the same bit of memory as its backing store. So when you create this map object, this isn't going to allocate any extra memory to store this. It will just be a view into the same, this vector of doubles A. And so if you change it through here, the element where however many ways in 100 ones down into A is going to get set to 1. Yeah, so this is useful. So if you've got a bit of data that you're using in your main application, say it's a vector, you're storing the data in a vector, but it's actually, and then you want to treat it like an Eigen vector and do some matrix multiplications on it or something, you can just do that and it won't do any extra memory allocation than is needed. So it can be extremely useful. So one thing that Eigen does do is it does, if you compile it in sort of the compiler's normal mode without specifying any optimization flags, it does a lot of checking. And this is great when you're developing your code. I mean, it will spot mistakes, and I would highly recommend running it in its sort of default mode, debug mode, at least occasionally when you're doing your development. But when you think you've got it working and you want to get the good performance, you need to make sure you turn on some optimization and that you supply the ndebug macro. That's one of the sort of standard C and C++ things that turns off all these checks. So for example, if you're using CMake to build your application, setting the build type to release will do this automatically for you. But let me emphasize, make sure you do check it occasionally. Okay, so let's do a little walkthrough of an example. So let's solve the diffusion equation. So it's quite simple. We have some temperature field, and we know that the rate of change of the temperature field with time is proportional to the second derivative of the field in a spatial sense, in the x direction. So it's some constant times grad t. And we're going to do this just in 1D. So this means that we can store our data in just a nice simple vector. And we're going to use an explicit method. Okay, so that means that each time step, the next estimate of the temperature field T can be solved by using some matrix A times the current state of the temperature field. So what we're going to need to do is create some initial vector for T, work out what our matrix A is, that's going to be this operator, and we're going to multiply T by A several times to solve forwards. So let's have a look at the exercise. Make file. So you need to make sure that the compiler is the one that you want. So G++ is last, which is the one that I've generally been using. check I've got my modules loaded. I do not. Load Eigen and GCC. Okay. Okay. Right. So what's going on here? So first we've got our include. We've got to include Eigen, and we've got some other bits of the standard library that. Sorry, I've started getting a bit more militant about my include files since this thing. It's generally considered to be a good practice. It's not essential to put the standard library includes first, and then any user libraries next, and then your current projects include files after that. But that's far from essential, and so on. So let's work with a fixed size of 12 elements, and we're allocating a vector to store our data, and we're going to have n squared of these because it's a square matrix in this particular case. So we're going to create a map to view this data. So we want a matrix of dynamic size of doubles, and we're going to map onto our stood vector that we created above. And we're going to say it's got size n squared. Okay. Now here, I'm saying that I'm assigning into A that it is the identity matrix of appropriate size. So I am zeroing everything except the diagonals, which are set to 1. I'm choosing what my diffusion coefficient is going to be. And now I'm doing my setup. So I am looping from I up to, but not including, the very end, the very last value. And I have to do my setup. So I am basically computing the appropriate operator here based on a very simple finite difference discretization of the diffusion operator. And then output A. Let's actually run this and see. You can see what's happening a bit better. So here is the matrix that I'm setting up. And what this is basically saying is that there's a certain contribution along the diagonal at the sort of the self contribution, and then there's the coupling to the neighboring points, and it's a bit different at the edges for the boundary conditions. So now I've set up my operator, my explicit operator. And that's where your maths and science comes in. And now I need my state vectors that's going to hit. So I'm going to start off by setting the vector everywhere to 0. So this head member function, this basically says get the first n elements, just like the head Unix command line tool would do. So I'm saying get me a view of the first n over 2 elements, and then let me look at it like an array, and now assign the value 1 into that. Then I'm getting a file, opening a file called a.text, storing it in F. And then this here is my, this is my time loop. So maybe I should be using T instead of I here. So I'm doing 20 time evolutions. And first I'm outputting to the console what the current temperature state is. So you can see that here, it's just the first half is 1s, and then it is some zeros. Then I'm outputting to the file this time my vector. So we've got this stored for later use. And then I'm doing my update. I'm saying that the next value of the temperature field B is equal to A times B. And then finally, outputting the last one, and I'm done. So I'm sure you all can plot numerical data right in your heads into a nice graph. We could get on and do that, but I'm sorry, I can't. I can't face doing that right now. So you can see it has evolved. The temperature field has gone from a step. Sorry, I'm looking at the wrong camera. A step function to something smoother. So since I have some paper right here, this is why I miss doing this in person with a whiteboard and stuff. I don't know if that came through well or not. Okay, so that is really kind of the simplest bit of solving of PDE you could ever hope for. Okay, where are my slides gone? Okay, so yeah, sorry, this is the very simple discretization. So it's showing what we've got here. So this delta term is the diffusion constant scaled by the time step and the spatial step. Yep, there we go, there's our matrix. But doing explicit methods is generally not going to be particularly good. They suffer quite badly from accuracy issues, and you usually end up having to take such a tiny time step if you want to do anything numerically interesting that it's very, very slow. And so let's have a look at an implicit method. So again, if the subscript is the time and the square brackets mean what position along the vector we're thinking about, let's do this. So it's a slightly different discretization from before. So instead of discretizing the gradient operator from the current time steps data, which makes it very simple numerically but suffers from accuracy problems, let's do that with the next time steps data. Let's compute that position. So what this means is that all of these t's on here are now unknown. So we have an equation that involves 3 different unknowns for every element of the matrix. So we can express this as a slightly different operator. We can say that the matrix acts on our unknowns to give us the things that we know t. So this means that we are solving a coupled set of linear equations, and a large chunk of scientific computing is about solving coupled sets of linear equations. So as you might expect, there is here in this. So I think what I'm going to do is going to sort of call it coffee break time now, and can have a look at if you want to have a quick look at this during the break, and then I can talk about what's happening here briefly after that. So let's restart. What's the time? It's 10:30. So let's restart at 11 o'clock on that. So I'm very happy for any questions right now, if anyone's got them.